All right, everyone, welcome. Today, we're going to talk about something that, well, it basically runs our entire modern world. It's a tiny, tiny device, but without it, none of the tech we use every day would exist. We are talking about the Mighty MOSFET. So, think about your smartphone for a second. Seriously, just look at it. How in the world do they cram so much power into that thing? It's kind of magic, right? Well, it all boils down to this one question. How do you fit billions, and I mean billions with a B, of little tiny switches inside something that fits in your hand? Well, the answer is a little piece of genius called the transistor. It's a microscopic marvel, really. These are the absolute bedrock, the fundamental building blocks of all modern electronics. Just think of them as super fast, super tiny light switches, flicking on and off to create the ones and zeros that make everything digital work. Okay, so here's our game plan for today. We'll start with why it's the ultimate switch. Then we'll get into the nitty-gritty of how it actually works. We'll look at the two main flavors you'll encounter. Then we'll see how the MOSFET stacks up against some of the other players out there. And, most importantly for you guys, we'll finish with your exam blueprint, what you really need to know. All right, first up, the ultimate switch. You know, before the MOSFET became the star of the show, there was another guy on the scene, the bipolar junction transistor, or BJT. Now, they both do the same job, they're both switches. But as we're about to find out, the MOSFET has some killer advantages that really change the game. So the MOSFET is part of this big family called FETs, which stands for Field Effect Transistors. Now, if you remember one thing from this whole lecture, make it this. It is a voltage-controlled device. Seriously, write that down. This is a huge deal. Why? Well, think about it. It takes way less energy to just apply voltage, a little zap, than to have a constant stream of current flowing to control something. That's the secret sauce. It's a big reason why your phone's battery doesn't die in an hour. And that brings us to our main event, the MOSFET. Yeah, the full name is a bit of a mouthful, I know. Metal Oxide Semiconductor Field Effect Transistor. But don't let it scare you. The name is actually a cheat sheet. It tells you everything you need to know about how it's built. And we're going to break that down right now. Okay, so let's get under the hood. How does this thing actually work? We're going to deconstruct the MOSFET piece by piece. All right, take a look at this picture here. Every MOSFET has three key parts, three terminals. You've got the source, that's where the current starts. You've got the drain, that's where it wants to go. And then you have the gate. The gate is the boss. It's the switch that decides if the current gets to make that journey from the source to the drain through this little pathway called the channel. Now remember the O in MOSFET for oxide? This is the secret ingredient. It's an unbelievably thin layer of silicon dioxide. Basically, it's glass, and it sits right between the gate and the channel. It's an insulator, and that is the whole magic trick. Because the gate is insulated, practically zero current can flow into it. All it needs is a bit of voltage to create an electric field, and that field is what controls the channel. This gives the MOSFET what we call a super high input impedance, and that's what makes it so ridiculously efficient. Okay, good. So MOSFETs basically come in two main flavors. You've got enhancement mode, and you've got depletion mode. And you gotta know this, they're pretty much polar opposites in how they behave. And you can actually see the difference right in their circuit symbols. Look here, see the one on the left, the depletion type? That vertical line in the middle is solid. That solid line tells you the channel is already there, it's built in. Now look at the enhancement type on the right. See how the line is broken? That's your clue that there's no channel there to start with. You have to create one. So here's the easiest way to think about it, and this is a great analogy. A depletion MOSFET, think of that as a leaky faucet. It's already on, current is flowing. It's normally on. You have to apply a voltage to pinch it shut and turn it off. The enhancement MOSFET is the opposite. It's a faucet that's shut off tight. It's normally off. You have to apply a voltage to turn it on and get the current flowing. This all leads to the big question, right? Why the MOSFET? I mean, why did this specific device basically take over the world of digital electronics? Your phone, your laptop, the massive servers that run the internet, it's all MOSFETs. And this chart right here, this tells you everything. The BJT, the older tech, is controlled by current. The MOSFET is controlled by voltage. We've covered that. That means it has that super high input resistance, sips power, way more efficient. But the real knockout punch, the reason you have a supercomputer in your pocket, it's size. You can make MOSFETs insanely, ridiculously small, way, way smaller than BJTs. And because they're so tiny, you can pack billions of them onto a single little chip. That's the whole game right there. Okay, everyone, pencils up, listen closely. This next bit is important. I'm talking exam important. Let's talk about exactly what you need to focus on to do well. Now, I've pulled this straight from your course materials. Look at questions 3 and 4 here. This is what you need to nail. You have got to be able to explain how both enhancement and depletion MOSFETs work. And you need to be able to draw their VI characteristics, the graph of voltage versus current. I can almost guarantee you this will be on the exam. It's a classic question. Master it. Okay, let's do a super quick final recap. What did we learn? 1. MOSFET is a voltage-controlled switch. That means it's efficient. 2. The magic is that oxide layer, the insulated gate. It gives it that crazy high input impedance. 3. Remember the faucets. Enhancement is normally off, depletion is normally on. And 4. They're smaller, faster, and use less power than BJTs. That's why they won the digital race. Simple as that. So I want to leave you with this one last thought. For 50 years, the MOSFET has been the undisputed king. It's powered everything. But we're starting to hit the physical limits of how small we can make them. So the big question for your generation of engineers is, what's next? What kind of switch is going to power the next 50 years? Something to think about.